Welcome to another problem with the physics tutor. This problem is Giancoli, 7th edition, chapter 11, problem number 2. And in this problem, we'll be dealing with a mass on a spring. They've disguised our mass on a spring as a car. The problem reads, the spring of a 1,700 kilogram car compresses 5 millimeters when its 66 kilogram driver gets into the driver's seat. If the car goes over a bump, what will be the frequency of oscillations? Ignore damping. So the first thing that we'll do is write out what we're given. We're given the mass of the car, which equals 1,700 kilograms, and I'll use the symbol m sub c for the car. Mass of the driver is 66 kilograms, mass sub d, m sub d for mass of driver. And then they tell us that when the driver gets into the car, we get a displacement, delta x, equal to 5.0 millimeters, which I'm immediately going to convert by multiplying by the conversion factor of 1 meter has 1,000 millimeters, to give me 0.005 meters. Now, in this problem, we're dealing with a mass on a spring, and they're asking us what is the frequency of oscillations as we go over a bump. Okay, so immediately we're dealing with a mass on a spring, because a car is really just the body of the car sitting on top of the suspension. It's like a mass on a spring, and they wanted us to determine what's going to happen with it as it moves up and down after being disturbed. So frequency has a relationship with period, which is 1 over period. So the frequency of a simple harmonic oscillator is the inverse of the period of that simple harmonic oscillator. We know from earlier that the period of a block on a spring is equal to 2 pi times the square root of m over k, where m is the total mass of the attached to the spring, k is the spring constant, and 2 pi is just a value, a constant value. This is the period. The frequency, as we can see here, is the inverse of the period. So that means if this is the period, then its inverse is the frequency. So the frequency would be 1 over 2 pi times the square root of the spring constant k over the total mass attached to the spring. So this is the relationship that we're interested in to answer this question: what will be the frequency of oscillation as this car and driver go over bumps? Now, you can see we're missing some information over here. We have the mass of the car, we have the mass of the driver, and we have the displacement caused by the 66 kilogram driver when they get into the 1,700 kilogram car. Okay, the car starts at some equilibrium position and then moves down when you get in it. You've all experienced this when you step into a car or you see somebody step into a car. You can see the body of the car actually lowers down as that person gets in. Okay, particularly if it's a small car and a large person, you might see a large displacement downward. That's simply the springs that are the chassis, that are the suspension of the car, compressing underneath additional mass. They're moving from an equilibrium position to a new equilibrium position. So you can imagine, here is the road. Here's our wheels, and we have little springs that go essentially from the axle up to our car. Here's our 1,700 kilogram car. Here's our springs that are keeping it off the axles of our wheels. And this is the equilibrium position of the car's mass before the driver gets in. Now, when the driver gets in, so this is no driver. When the driver gets in, we're now going to have a situation where the springs are compressed. And you can see we now have a new equilibrium position. This distance right here, this would be our delta x. So this is with driver. So this was 1,700 kilograms. And then we added on top of this our 66 kilogram driver. Okay, so we've changed the position, the equilibrium position of our mass on a spring system. So that's how we're going to model this. We're going to model this whole situation like it's a mass on a spring. Before we can figure out the frequency, though, we need to find that K value. So we're missing this piece of information right now. So step number one is going to be to use this information right here to determine our K value. So step number one, find the K value of our spring. Okay, so that's what we have to do first. Okay, so how can we do that? Well, we can use this concept right here. We're initially at some x equals 0 position. You can imagine that this position here, this initial equilibrium position with no driver, is x equals 0. And then we put a 66 kilogram mass on top of the car, and that causes the springs to compress delta x, or 0.005 meters. So when we get to this new equilibrium position, we're again in a static situation. The car isn't oscillating up and down here. We move from our initial equilibrium position to a final equilibrium position, and we're no longer moving. So once you've got in the car and you've compressed the spring, the acceleration is 0. And so the upward spring force and the downward force of the driver can be set equal to each other. If you think about what's causing this change in distance, it's the addition of this 66 kilograms. So any change in the spring force from this position to this position is going to be equal to this 66 kilograms. So essentially, I can write that we have a sum of forces in, I'm calling up and down the x direction here, in the x direction, that's going to be equal to the spring force in the upward direction. The spring force is negative kx, minus the gravitational force of our driver, mass driver, times g, so this is a force and this is a force, is going to be equal to 0, because when we're at this equilibrium position, there's no acceleration. So our acceleration, our value here, ma, becomes 0. So I want to find k, so I can say negative kx, and now I'm going to add mass of the driver g plus mass of the driver g to both sides of our equation. So that's going to be equal to mass of driver times g. Negative k, I'll then divide both sides by x, our displacement, mdg x. And then I don't want negative k, I want k. So I'll say k is equal to negative mdg over x. And now I've isolated k, the spring constant, which is what we wanted to do in our first step, and now I can plug in some numbers. I can say negative 66 kilograms times 9.8 meters per second squared divided by, now if this was our equilibrium position and we've moved downward, I'm choosing down to be the negative x direction, then our displacement is negative 0.005 meters. And this will result in newtons per meter, which is the units for K. And we will discover that we end up with 129,360 Newton meters for our spring constant. This is the value of K, our spring constant, that we need to place in this formula. Now that we have this value here, we can go and actually answer the question they ask. What is the frequency of oscillations as we go over a bump? In other words, in this mass on a spring system, how are we going to oscillate? Now, the thing you have to be careful with here is the driver is now in the car. So the total mass is what's going to be oscillating up and down to give us this frequency. So step number 2, find the frequency of total mass on spring. Okay, so this is our final step to get us to our final answer. So in this case, we can fill in. We can say the frequency is equal to 1 over 2 pi times the square root. And this whole thing is under the radical here, so it's 129,360 Newton meters divided by the total mass, which is 1,766 kilograms. Note I'm using the total mass, the 1,700 kilograms of the car and the 66 kilograms of the driver all combined together, because this is what's going to oscillate up and down as we move along. And if you plug this into your calculator, you should come out with an answer of 1.362 hertz, or oscillations per second, which is approximately 1.4 hertz. And if you were to look up the answer to this in the textbook or wherever, you would find that this is the answer that they give. And if you go back and look why that's the answer that they give, rounded to 1.4, it's because we have 2 significant figures in 1700, 2 significant figures in 66, and 2 significant figures in 5.0. So our answer ends with 2 significant figures. I hope this explanation was helpful to you, and I'll see you in the next problem. Have fun physicsing.